Today we're going to talk about position and time graphs of accelerating objects. So before we talked about objects with a constant velocity, these objects are going to be accelerating as they move, meaning that we are speeding up or slowing down. So when an object is accelerating, the position time graph isn't linear, it's curved. If the acceleration is constant, then the curve fits a quadratic. And you've learned about quadratic functions and parabolas in math, hopefully. If we need to review that, please let me know and we can go through it. The skills that we need are going to be to analyze these are the same as we used before. So we're reading the graph the exact same time. And finding the slope of the graph is going to give us the velocity at the time that we're looking for. So this graph is going to show the position of a plane as it takes off. Obviously, a plane does not move at a constant velocity. There's no straight lines here, but it does move at a constant acceleration. It follows a parabolic path. Now we're going to try to look at our graph and determine the position of the plane after 2 seconds. So at our time of 2 seconds, we are 10 meters west. At 4 seconds, we go up and it's about 40 meters west. 6 seconds, we go up to here and we are at about 90 meters west. And then 8 seconds, we are at the top with our 160 meters west. So reading it's the exact same thing we did before. With a curve, instead of a line, we can't actually immediately find the velocity just by calculating the slope. So first we have to draw a tangent line, and that is a line that touches the graph at just one point. Tangents only like to touch with one finger. Since the slope of a curved graph is always changing, the slope of the tangent line tells us the instantaneous velocity at just that point in time. So we're going to go through this together. Don't worry if you feel a little lost. But steps to find an instantaneous velocity at our time for an accelerating object on a position time graph is that we're going to find the position of the object at this certain time, which is what we were just doing. Then we're going to use a ruler to draw a line that only touches the curve at that one point. And that's going to be your tangent line. If you don't have a ruler with you, you can use the edge of a paper, you can use a credit card, your driver's license, whatever you got. And then you're going to find the slope of the tangent line. And that might be easier if you extend the line farther to hit more points, because if you can just find a spot where the line crisscrosses an intersection, then you're not going to have to guess at what time it might be or what decimal you might need. You want to try to hit something where you have a box, a graph box that intersects. I'm making all these hand motions that you can't see. So if we're looking at determining instantaneous velocity at 2 seconds, here we have 2 seconds, and we drew a tangent line. So we want the line to touch at 2 seconds, but not touch anything else. And I'm not going to go super far with it. Like, I don't need to draw this line all the way out here, but just to where I can get two intersecting points of my graph lines so that I can calculate easily what's happening. So on a piece of paper, if I draw this out, I would hit down here at 1, 0, and then up here also at 320. So using that with our rise over run equation, my D2 was my 20 meters west and my D1 was 0 meters west. And then my time ended at 3 seconds and started at 1 second. So when I calculate that, the instantaneous velocity at this spot where I'm touching 2 seconds on the graph is going to be 10 meters west per second. If this is complicated to you, that's totally fine. We're going to go through a few more examples, but also feel free to jump on a Google Meet where I can draw these out and show you the actual process. So if we're looking at 4 seconds, let's come back here. So I want to touch the line at 4 seconds, but nowhere else. So I'm going to put my ruler up against that edge and then draw a line until I've connected some spots. So I might have drawn my line extending out both directions, but I can start right here at my 320 that I had already started at. And then my spot also connects up here at 560. So I would use those numbers to calculate my velocity. And then I wanted it at 6 seconds as well. So here's my tangential line, meaning it only touches at 6 seconds and nowhere else on the graph. And I can use 560 and 120 for my spots there. So here's the math solving those out. I'm taking my points, my d2 minus d1 over t2 minus t1, and I'm calculating that at 4 seconds, my velocity is 20 meters west per second. And then at 6 seconds, I'm at 30 meters west per second. So on a calculus note, I am not sure if any of you guys are in calculus at the time, but if you know the position function, the instantaneous velocity can be found by finding the derivative at t, but we're just going to do it with our tangential lines because it's just a little bit simpler and not everybody is in calculus. So if you have questions, please come to Google Meet and we can draw some practice ones up together and work on them at the same time.